So far, we've talked about collections of objects that are moving together when they have the same acceleration. So, like a line of carts all in a row, um, if you push on one, they all have the same acceleration along the surface. Now we're going to talk about collections of objects that are moving together with different accelerations, and I'll show you an example of when this would come up. So if you had, say, a ledge with a pulley over the ledge, um, and a cart here, and then a cable going over the pulley connects that cart to a hanging mass. And I'm going to do this as an example, so let me give these some masses so we can do math with it. Let's say that this one is 5 kilograms and this one is 1 kilogram. And let's say we want to calculate the acceleration of one of these two things. Well, notice that the motions depend on each other. But the 5 kilogram mass is going to move along the x-axis, you know, and the 1 kilogram mass is going to move vertically, okay? So those accelerations depend on each other, but they're in different directions. Okay, so what's the approach we're going to take for this? The first thing we're going to do is we're going to draw a free body diagram and use Newton's second law for each of these two objects individually. So Newton's second law, you have to remember a free body diagram for every Newton's second law. For each object. And let's call the accelerations. So the accelerations are going to depend on variables A. So that's just like normal. But then the second one, we're going to call that variable something else. Let's say A2. Okay. So now we have it expressed in two different accelerations, but we haven't yet taken advantage of the fact that we know that the acceleration of one is going to depend on the other in some way. And so the second step is if A is positive, A2 has a sign that's specified. And so you're going to substitute A2 equals, plus or minus A, depending on which sign it is, into the equation that has A2. And then the last step is now you have a system of two equations for two variables. And you can do that by substitution. Okay, so let me go back to this example that I drew, and we'll see how this works. So I'm going to use that example that I drew above. And one thing I want you to notice is, it's not going to be an issue yet, But these two coordinate systems that you use for those two individual bodies don't have to be the same. In this case, they are going to be, because this is a rolling and sliding problem along a horizontal surface. So these will be the same. But you could also imagine this 5-kilogram cart moving along an incline. And then we would want to use a rotated coordinate system for the rolling cart and the standard coordinate system for the hanging mass. And you can do that. Those two coordinate systems don't have to be the same. So I'll show an example like that after I'm done with this one. Okay, so the rolling mass is the 5-kilogram. And so what does its free body diagram look like? There's a weight force. 5 times 9.81 is 49.05. And then we have the pushing force, N. And then we have the pulling force from the cable. We'll call that T. And there aren't any other forces acting around the boundary, so we know we're done. And so now go to Newton's second law. And you have 0, negative 49.05. The normal force, the pulling force, and these are equal to the mass times the acceleration, so 5 times. Now this cart can only accelerate, can only move along the x-axis, so I'm going to call this one A0. Okay, well, the x equation says that t is equal to 5a. That has two variables, so we can't solve for it yet, but we are going to set it aside. This is going to be the first of our two equations that we're going to solve as a system of equations. So I'm going to call that equation star. We're going to solve that with an equation 2 star. So now we'll go to the free body diagram of the hanging mass. That's the 1 kilogram. There's a weight force of 9.81. And then the cable is pulling up with a magnitude of T, because it's the same cable as the other one. And that's everything in the free body diagram. So now Newton's second law says 0, negative 9.81. Plus 0t is equal to the mass times the acceleration. Now, you have to think, what's the acceleration of this one? Okay, this one is only going to be able to move up and down. So that's going to be in our y direction. So I'm going to call this 0a2. So far, we've just figured out the directions of the accelerations, right? But we haven't made a connection between the accelerations of the two, because one depends on this variable a, and the other one depends on this different variable a2. Okay. Well, the useful equation for this one is the y equation, and it says negative 9.81 plus t is equal to a2. But now here's sort of the key step. Like I said, we still haven't dealt with the fact that these accelerations are connected. So now you have to think, go back to this system. If this 5-kilogram cart moves, let's say, an inch in the positive x direction, where does the 1 kilogram mass move? So if the 5 is moving in the positive x direction to the right, the 1 kilogram, the mass, is moving 1 inch down in the negative y direction. Okay, So a positive X motion of the rolling cart connects to a negative Y motion of the hanging mass. All right, well, so what we have to do is recognize that if A is positive for the 5 kilogram cart, A2 is negative for the 1 kilogram cart. Okay, and so that tells us that A2 is equal to negative A. Now put that into the equation, and that'll give us our second equation for the system. So negative 9.81 plus T is equal to, substitute A in here, and you get negative A now. And this is our equation 2 star. Well, now look at our system of equations. We have two equations and two variables, T and A. And we just have to solve that by substitution. So I'm going to solve star and 2 star by substitution for the variables T and A. Okay. Well, from the equation star, we see that T is equal to 5A, so I'm going to substitute 5A in for T in the second one. And we get now negative 9.81 plus 5A. I replaced the T with the 5A in the second one, is equal to negative A. And move this stuff around, and you get that 6A is equal to 9.81. And so A is equal to 1.64 meters per second squared. Now you can use that to calculate T. So just go back to whichever one of these equations looks, these two equations, start equations, look simpler for finding T. In this case, I guess that's the first one. And T is equal to 5 times A. So let me calculate that. 5 times 1.64. We get that T is equal to 8.20 newtons. So the tension force in this cable is 8.2 newtons. Notice that that's not the weight of either of these two things. You know, it's more complicated than that. It's less than the weight of that hanging mass because there's acceleration that that's involved. And the acceleration, then, if you want to know, you know, the acceleration vector of the 5 kilogram cart, plug this value of 1.64 back into your acceleration vector here. And you get an acceleration vector of the 5 kilogram cart of 1.640. Or another way to write it would be in that direction, 1.64 meters per second squared. So I would recommend that when you first start doing problems like this, you sort of explicitly think of these 3 steps to go through. Later on, you probably won't have to be as careful about that. You'll sort of do it naturally, but for now, I would just look at these steps as you go. Just try to ingrain those in your head. Okay, well, I mentioned that sometimes you're going to use different coordinate systems for the two bodies. So I also want to do an example like that. Okay, so let's say we have an incline, and let's say that this incline is at an angle of 20 degrees. And let's say that, again, we have a pulley here connecting a rolling cart to a hanging mass. Let's say that the hanging mass is 2 kilograms. And this one also, I drew it a little bigger, but let's say it's also 2 kilograms. And we want to know what's the acceleration vector of the cart and what's the tension in the cable. So that's that T value. Well, in any rolling and sliding problem, we're going to want to use a coordinate system where the y-axis points straight out of the surface. So when we're dealing with the cart, we're going to use a rotated coordinate system. And on the hanging mass, there's no reason to do that, so we'll just use a normal coordinate system, and that's fine. Each one of these can have a different coordinate system. All right, well, I'm going to start with a free body diagram of the cart. Okay. So we have a weight force straight down. 2 times 9.81 is 19.62. We have a pushing force from the surface that now is not parallel to that weight force. I'll call that N. And we have a force, a pulling force from the cable that way. And now we have everything in there, so we can go to Newton's second law. Notice, compared to this rotated coordinate system, that pulling force is in the negative x direction, so negative P0. The normal force, like it always is just 0, positive N. The weight force is 20 degrees past 270 if you start at the positive x-axis and go to the weight force as if it was a vector problem from the vector assignments. And so this is going to be 19.62 times cosine of 290, 19.62 times sine of 290. And all that is equal to the mass times the acceleration. And in these rolling and sliding problems, it's always going to be that. Again, since all we want is this T and this A in this problem, the Y equation doesn't come into it. I think I am going to calculate that, though, to show you one thing here. Okay, so the X equation says minus T plus 19.62 times the cosine of 290. So that's plus 6.71 is equal to 2A. And so that's going to be the first start equation for the system we're going to solve. As an aside, I want to show you something about Y. I'm not going to star this or box it because it's not going to come into solving this problem. But I think one thing that you've seen pretty often in these problems is that the normal force is just equal to the weight. That doesn't have to be true, and there are a lot of ways that those don't have to be the same. This is one of them. This thing being on an incline, our equation says n plus 19.62 times the sine of 290. So that's minus 18.44 is equal to 0. And so if you calculated that normal force, you'd get a normal force of 18.44 newtons, which is not the same as the weight of this cart. The weight is 19.62. So those normal forces, you can't just assume that those are going to be equal to the weight. You always have to calculate them if you want them. That would come up for sure in like a friction problem. If this was, if instead of being a cart on wheels, this was a block with some known friction coefficient, you'd have to calculate that n. You couldn't just assume that it was going to be equal to the weight. Okay, so now let's go to the free body diagram of the hanging mass. We have a weight of 19.62, a pulling force from the cable that's T because it's the same cable. And then Newton's second law says 0T plus 0 negative 19.62 is equal to the mass times the acceleration. Okay, so what's the acceleration of this hanging mass? It can only go up and down. So I'm going to write that as 0 A2. So the y equation says T minus 19.62 is equal to 2A2. Well, now we have to substitute in for A2 so that we only have one thing representing these accelerations. Notice that if the way that this ramp is oriented, if we have a motion of say that the cart moves 1 inch in the positive x direction, this time the hanging mass moves 1 inch in the positive y direction. So last example problem, one was positive and one was negative. This example problem, one positive means the other one is also positive, even though, we're dealing with the x and y axes. But so that tells us that let's say A2 is equal to positive A. And so that substitution just says T minus 19.62 is equal to 2A when you make that substitution. And there's my second starred equation. Well, now I have the two starred equations, and I can substitute one into the other one. So let's say that equation 1 star, if I rearrange it, says T is equal to 6.71 minus 2A. So now I'm going to substitute that into equation 2 star. In place of the T in equation 2 star, I'm going to put in all this stuff that's equal to T. So we have 6.71 minus 2A minus 19.62 is equal to 2A. Um, and so we have on the left side of the equation, negative 12.91. And I'll get all the a's to the right side of the equation. So we have is equal to 4a. And if you solve for a, you get that a is equal to 3.23 meters per second squared. Now you can use, let's say, equation 2 star to find t. Just plug this a value into the a in equation 2 star. And you get that t is equal to positive 19.62 plus 2 times what we just got for a. And so this t value is equal to 26 point, let's see, is that right? Oh, no, that's not. Okay, I made a mistake. I just missed I forgot the negative here on the A. Okay. But then the approach that I was using is right. So we have 2 times negative 3.23 plus 19.62. And you get that T is 13.16 newtons. And again, you might think in this problem that the tension in that cable is going to be the weight of this mass or something. It doesn't work like that. It's more complicated than that. So the tension in that cable, the strength of that cable you would need for it not to break, say, as these are moving, is 13.16 newtons. Now you can plug, if you want to know the acceleration vector of the cart, plug this value of A back into your acceleration vector that you used in Newton's second law, this thing. And you get an acceleration of negative 3.23 for x, 0 for y. Or in other words, an acceleration up the ramp of 3.23 meters per second squared. So this 2 kilogram mass is enough to make the 2 kilogram cart accelerate up the ramp toward the pulley.